You could just imply that from the sheet because if sigma of theta hat is sigma over square root of n, and sigma squared, which is a variance of the estimator, is sigma squared over n, right?
Maybe. I'm not quite sure. I'll stick to this. This is definitely how it pops out. I mean, you might be on the right track there, but I like this way. This is how I've always done it. It's never led me astray. So this is how you prove the variance is 1 over 12n. So it's the MSE of y bar. I'm just putting y bar here, I suppose.
I mean, I think that's good to know anyways, just in case, because he could ask us to prove that y is a variance.
Yeah. So that's why this is 1 over 12n, because look at the variance of not y, or any of the yi's, but y bar, which we showed to be 1 over 12n a second ago. Cool? All right. And then plus 1/4. That's your MSE. Cool. All right. We got 2 more on this test. Suppose that theta hat is an unbiased estimator for theta, and that variance of theta hat is larger than 0. Show that theta squared is not an unbiased estimator for theta squared. Ooh.
How did you get to from here to the 1 over 12?
Each of the yi's has a variance of 1/12. And we found that from using the kind of erased it. Remember the uniform distribution for a to b has mean a plus b over 2 and variance b minus a over squared over 12.
Oh, okay.
So if you do theta plus 1 minus theta, that's 1.
Okay.
Square, you get 1 over 12. So each of the individual yi's has variance 1 over 12. We're recording. Very good. Theta hat is an unbiased estimator for theta. So theta hat is unbiased. Estimator for theta, which is to say expected value of theta hat minus theta is 0, or you could say expected value of theta hat equals theta. Okay. And the variance of theta hat is positive. Show that theta squared is not an unbiased estimator for theta squared, okay? I don't know. Theta squared, theta hat squared.
Show that
We want to examine this guy.
Not
So they said something about the variance. They said the variance of theta hat is positive. Whenever you see variance of theta hat and you see an expected value of theta hat squared, you got to be thinking that formula. Variance, let's say VAR, to be consistent, VAR of x is equal to the expected value of x squared minus the expected value, of x squared, right? Now, what do they tell us about the variance of theta hat? They said variance of theta hat is positive, but it would also be equal to the expected value of theta hat squared minus the expected value of theta squared, theta hat squared. What is the expected value of theta hat?
You.
Nope.
Is theta?
It is. Why do I know that?
Oh, because it's
it's
unbiased.
It's unbiased.
Yeah, okay.
Okay. All right. We're going somewhere here. This is getting something. We might know. Maybe. Oh shit! What is this? What does this represent? What does expected value of something minus the thing it's trying to estimate give you? The
bias.
The bias. This is the what?
Okay, it's also bias.
This is the bias.
Gotcha.
But what do we know about this? We want to show that it's not. We want to show that it's biased, not unbiased, right? We want to show that it is a. Show that it is not an unbiased estimator. How is this not unbiased? What do we know about this quantity?
Well, it can't equal 0.
Yeah.
Why not? Why couldn't it equal 0?
Wouldn't it be biased if it did?
Well, yeah, but that's what we're trying to prove.
Okay.
We're trying to prove that it's unbiased. What do we know about
would be
No, it
greater
says
than
show
0.
that-
why?
Oh, well, that's what was given to
They
us.
told us the variance of this guy was positive to begin with. So this whole thing is larger than 0 the entire way through.
Oh.
So we're using two things here, and this is where both parts of this problem come into play. And this is a very difficult problem because all the students are not seeing how those things are coming together. We started with the fact that theta is an unbiased estimator for theta. That is, the expected value of theta hat minus theta is 0. Equivalently, the expected value of theta hat is equal to theta. Then we want to try and figure out, we want to show that this is not 0. Show that this is not 0. So we're probably thinking, okay, where would I begin? They mentioned the variance. That's like, hint, hint. I want to use a formula that involves variance of theta and the expected value of theta hat squared.
Gotcha.
Gee, I wonder if there's a formula. Oh, yeah, there is. This one, right? Smart to think, okay, they're dropping hints here on the variance. We see this quantity here. Wait, where have I seen this before? Oh, right, in the variance formula. So we're going to want to use this, right? So we drop down. We're just going to, this is just one you should memorize and know.
Okay.
We're going to drop down to this formula, replacing every instance of x by theta hat. So the variance of theta hat, which we know is positive, was given to be positive. We'll make that jump, and then we'll make that conclusion in a minute. Is the same thing as expected value of theta hat squared minus expected value of theta hat, that quantity squared. What is expected value of theta hat? Well, they told us theta hat was an unbiased estimator, so expected value of theta hat is theta. They told us that theta hat was an unbiased estimator, that is to say, expected value of theta hat is theta. Cool?
Yeah.
Then what does this represent? What is this formula? Oh, that's a bias formula for theta hat squared. Well, how can I be sure that it's positive? Because this is the variance formula, and they told us the variance was positive. So it's using all that information together to give us that this is not an unbiased estimator. Make sense? Are there any questions about that? So I'm kind of using three things here. We're using this guy. This is the one thing we're using. We're using this guy here. We're using the fact this is number 2 that was given to us. We're using that here. The last one we're using is just knowing this formula. This wasn't given, but this is a formula you should know. This is my expected or my bias formula. So as soon as I see that, I should go, oh yeah, it's my bias formula. That's the one I'm trying to show. Over here is not 0. Cool? That's a kind of a hard proof question. That'd be a lot of points. So probably, well, maybe it was a few points because, I don't know, he didn't want to penalize other people who didn't know the hell they were doing, which is nice, right? You saw a problem like that, you might shit your pants, but you'd be like, okay, I'm not losing 12 points for it. Suppose y is a binomial random variable with n trials. When we use the normal approximation to the binomial, we make a correction factor of plus or minus 0.5 in order to get our better approximation. For each part below, indicate the appropriate. Oh, okay, this is boring. Yeah, this is okay. We'll do that then.
I see that. Do you guys want to see that one, or do you want to see another one?
No, skip it.
Skip it.
Yeah, let's skip it.
Yeah, make sure
that's easy.
Just
We
draw
can
the
do that.
bars.
That's just the same thing about the bars of what he was
That's
saying.
fine.
And you do. There's 41. So if they wanted less than 41, you would say 40.5.
You want to look at exam 2 to see if there's any.
Sure, it looks like if exam 2 has more
Exam
compensable
2
stuff.
has, more of the...
And moment stuff, right?
Yes.
Which we might want to run
Although
through
they
really quick.
never went over moments in this one, so I don't know who's going to be doing with moments on the
Okay.
exam or not.
Yeah, I don't know which one of these.
This one doesn't go over
I have a good
moments
idea.
at all.
I probably have a
think
good
you
idea.
skipped over them.
Huh?
Yeah, I think you just skipped over them, so in this semester, or for the exam at least.
But I'm saying that in the exam, have we covered everything on this exam in class, or
Shit.
Yeah.
or was it like
For exam 2?
your exam 1 and 2 was the same thing as our exam 1? Not 1 now. Is that what? That's
Let
what
me
I'm
check
saying.
the exams. Let me check my exam.
Because we only went to the end of chapter 8, so I'm saying does this go further to chapter 8?
I don't know. I'll check.
You know what I'm saying? Like, 'cause chapter 8 is a big one.
Yeah. I mean, chapter 8 is covered in, or you know, is a big part of it. But here we go. We would really should have this one. Let's see.
What do you think, Andrew?
So yeah, it's
I kind of
just
want to talk more about confidence intervals.
it's a
Unless you-
lot about. See, this is point estimation, I believe. So this
That's
is
my
point
system.
estimation.
Oh, yeah.
We're gonna go to Wendy's.
Alright, sounds good.
Alright, bye guys.
See you.
Bye.
Alright. This is relative efficiency between bias and bias estimators. Problems you didn't have.
We didn't learn that, right? Relative efficiency.
Relative efficiency. I don't remember him going over it, but it definitely was in a part that we covered. So, but none of the questions I've gone over have to do with relative efficiency. It's not difficult, but
Well, let's just make sure you went over it.
yeah, confidence
I think he
intervals.
went over that.
Pretty much a lot of his confidence intervals going over that stuff.
Yeah, relative efficiency is chapter 9. So
Yeah, what is assignment 5? I haven't even gotten to assignment 5 yet. I don't know what's on it.
I guess like confidence intervals,
Let's see.
small sample confidence intervals for variance, sigma squared.
I'm gonna pick out some confidence interval questions. We'll do that.
What's that?
Okay.
We'll do some confidence interval questions.
It's fine.
Why don't you pick, since we don't have that much time, pick like some really hard ones.
Sure. We
Yeah.
wish to estimate the difference in proportion. Actually, not proportion. Let's do
Th-
means.
With this, he usually puts easier in the front, harder towards the back.
Okay.
So
A random sample size of 17 was taken from a population n equals 17. First of all, this is already hinting that this is a small size.
yeah, so it's gonna be a T.
We usually take that to mean n is less than or equal to 30, or maybe less than 30. 30 is where again,
Yeah.
it's for some universities it's 25, some universities it's 40, so 30 is
In
our
this book is 30.
30. So that's our magic number. 17 is small enough that we're going to use the t distribution. So that's a hint here that when you see n equals 17 automatically, just write down t distribution because it's small sample size. You'll get points automatically.
Okay.
Oh yeah, if n equals, it says it might say on the paper if n equals 30, but sometimes it'll say n equals 25. You use essential limit theorem. So
Okay.
Oh, okay.
This sample produces a sample mean of 68.3, and a sample standard deviation, for which we use s of x, to 5.4. Find a 95% confidence interval for the population mean. Holy shit, this is not that hard. Here's the formula you need to know: plus or minus t star
it's like an example. So actually, this isn't hard.
s
It's pretty easy.
x
So
over
you
square root
have a
n.
good one that you might want to see.
So,
Honestly, I kind of want to do moments.
by the way, I want to reference this about a calculator. 68.3 plus or minus t star. What that corresponds to, this is where you need a t table. So, how many degrees of freedom do we have? 17 sample size. So degrees of freedom is what?
16.
16. We go to our t table, 16, and we want a 95% confidence interval.
0.95. And we don't have to subtract.
Careful, you need to
that,
make sure you're in the right tail here, Eddie. So scroll up a little bit. That's just the right-hand tail. So if you're looking for a 95% confidence interval,
Want a 0.025,
you're
right?
looking for 0.025 in each tail.
So that corresponds
Are
to
you
2.120.
so yeah, for
2.1.
confidence intervals is
I
always
can't see
1
first.
minus
2.12.
the confidence is always 1 minus alpha, and then
No.
it's not always at that.
This is alpha, right? You might consider this alpha.
Yeah.
It depends what you consider alpha. I mean,
He considers that alpha.
the
What-
total of the tails
Oh, what I
is
was
alpha
saying.
too.
Yeah,
Gotcha.
and then
So yes, then 1 minus alpha.
Yeah, this is, and also we're only doing 2 tail tests. He said no.
Seemingly there's no one tail test
So-
so far. So yeah, times s of x is 5.4 over square root of 17, whatever number that gives you. You're done. Now let me show you the calculator. Same thing.
As
Yeah, same thing as before. Stat
Mm-hmm.
over to tests. Go down to t interval, and then you don't do. There's two ways to input. There's data. That's if you have a list. If you ever
Oh,
stat
you have
list.
to create one.
Don't do that.
Yeah, okay.
Then go. So instead of doing list, we do stats, which means we just plug the information we get. So x bar was 68.3. S sub x was 5.4. Sample size was 17. Confidence interval only 1.95. Calculate, and it spits it right out.
Awesome.
Perfect.
All right.
So that's all in the stat over to test.
We're gonna do a moment question, right?
Yeah, could we go over some moments real quick?
Okay.
Let me go to assignment 1.
Like moment
okay.
generating functions.
Yeah.
Here, let me find it. It's gonna be in the book, so I don't know if you have the.
Yeah, I'll look for like.
I have the book right here.
Yeah,
what
so
questions?
6.72, 74, 80, and 100. So it's any of those, and he like gave you.
Okay, those are the ones that were in the turning for grading.
Yeah, so there's only like 4 or 5 problems, so I guess you scan through them, see which ones.
Sure. Which one? 6.74.
6.72,
Okay.
4, 80, 100.
Would you consider those harder? Would you consider the ones he asked for to turn for grading harder than the ones that weren't turning for grading?
Well, that's
I
not
didn't-
moment.
I didn't really go over.
No, you didn't?
too much.
This isn't moment stuff. This is order statistics.
Yeah, the order statistics. But
We see how little we know about it.
What's up?
You see how little we know.
There's
Uh,
like one little topic about moments.
Yeah, it's like one little topic, but
He's
he's
like,
going to
put
be
it
on
in
this
there,
side.
but-
all right,
Yeah.
order statistics kind of drives me nuts. You might so it tends to be the case that they ask about the min and the max, for which there are some formulas here.
Yeah.
There's a few on there.
I kind of understood this pretty
You
well.
kind of understand it now? Oh, that's good.
So
Yeah, I know
was
like
able-
confidence intervals pretty well. That's why I
Yeah.
kind of skipped 5.
Yeah, that's cool. I kind of understand this a lot better, but I mean, you could probably give me some clarity.
Yeah, this is the. So this
Oh,
is
yeah.
the.
Do you know? Because, bro, with me, it's always hard to remember the difference between which one is a distribution function and which one's a density.
Well, it's fine because there's
Yeah.
one's a derivative.
Yeah.
I know.
Yeah,
I know
once
the
you do
derivatives.
the other, or once you
Sometimes
you know
I
which
forget-
one is which,
Sometimes I
though?
forget which one to use or which one's which. Yeah.
I mean, I don't know if you're good with.
That's what it
I
is.
don't know how. I'm good with like certain like little acronyms and stuff
Sure.
like that. And I just remember I goes before E, so distribution goes before density, and capital goes before lowercase. So capital F is distribution, lowercase f is
This is
density.
density. Yeah.
I just kind of remember it like that.
Yeah,
That's
that's
what I
all-
remember.
yeah.
It says.
Okay, so the probability density function. Find the probability density function. So this is y are independently and uniformly distributed over the interval 0, 1. So
What problem is
6.72.
Okay.
u1 and u2
Mhm.
are both uniformly distributed over the interval from 0 to 1.
Okay.
Okay. So what does the uniform distribution look like? Remember, I told you it looks like this little rectangle, right?
Mm-hmm.
A to B. And what's the height of this rectangle? It's a good question.
1?
It's not 1. What's the total area of the rectangle?
One.
That's 1.
Okay.
What's the width of this interval?
width? Is this
A
A
plus
plus
B.
B?
Not A plus B. This is where you want to say
B
minus
minus A.
A. B minus A, right? So if the width is B minus A,
minus
what
A.
should the height be so that the total area is 1? This is basic geometry. Here we go. Width, length times height, or width times height is going to equal 1. We know the width is B minus A. So what should the height be so that this equals 1? Solve for H. What would you get?
Oh, 1 over B minus
1 over B minus A. In this case, yes, you're right. It's 1, but I thought you were saying 1 because it's always 1. The height is not always 1. It depends. If you're looking at the interval, uniformly distributed over the interval from 3 to 7, then this rectangle will have a height of 1/4. How wide is the rectangle? 4. How tall is the rectangle? 1/4. So
Okay.
the total area is 1/4.
Gotcha.
So you were right by saying 1 in this case,
but
the
that's
width
still
is
good
1.
clarity.
Right.
Okay.
Good. So the height is indeed 1 for this case. So that means the density function is 1.
Yeah, and then I think he's gonna give us that table as well, like I said earlier.
It gives us
Yeah,
a table.
right. I'm sure it is. Yeah.
So for
Density
uniform,
functions.
yeah, we just plug in 1 over.
Does he give you the CDF though? No, doesn't seem he does. Not there, he doesn't. So what would the CDF be?
CDF?
Yeah, this is the PDF. How do I get the CDF?
Oh, you
So
integrate it?
Integrate it,
left,
right?
yeah.
And you integrate from, I guess you integrate from negative infinity to.
He does from 0 to 1 because of the interval.
Right,
Or
so
he
technically-
integrates from the intervals.
You're
is
supposed
what
to.
I
Here's
noticed.
what you're technically supposed to do. And this,
Okay.
this really should be f of u du,
Okay.
and you use y here.
Okay.
The CDF is what's the probability from all the way back up until some point y. That's what a CDF is.
Okay.
This would be f of y. Now, technically our distribution doesn't start until 0, so we can say
Okay.
0, right? And so this would just be, what is f of u? We know f of u is 1.
Mhm.
Plug in, integrate this guy, you get u. Plug in y, plug in 0 for the difference, and you just get y.
Okay.
Now, you got to be a little careful about this because it should be a piecewise it should be a piecewise function. F of y equals the following. It's 0 if y is less than 0. It's y if y is between 0 and 1. And it's 1 if y is larger than or equal to 1.
Okay.
Why is it?
Why does it do this?
Why is it always? That always confused me from stats 1. Why is it y if y is greater than or equal to 1?
Why is it 1?
It's like
Yeah, why is it 1?
This is because, let's put it this way. You're reading left to right. It's like I'm taking a tractor and I'm driving over this plow of land or I'm digging up the land. How much, if I'm going left to right, how much of the area have I dug up so far?
None.
None.
Oh, okay.
How much of the area have I dug up when I get to this point?
All of it.
All of it.
Gotcha.
Hence 1. Make sense?
Okay.
It turns out this is such a nice one that how much have I dug up here? Why? Wherever I am. Turns out because this is such a nice shape. This is a square from 0 to 1. How much have I dug up if I've gone 0.3 to the right? How much? I would guess 0.3. If it was something like this, I wouldn't start digging anything up until 3, and even then I wouldn't dig it up at quite the same rate because it's a little bit shorter. Make sense?
Okay.
Makes sense. All right. So I don't know what you put here. I would just say y. So for the min, it would be n times, or rather, how many
2.
2. 2 times 1 minus y to the 1 times 1. I think that's the answer that we're looking for.
Yeah, it was.
Yeah, they use U, but it's the same thing.
Mhm.
Yeah.
Did I get some clarification,
Mhm.
Brian?
Yeah. And then for the max, it's 2 times y to the 1 times 1. All right, let's do 6.74 then, or what was find expected value?
Yeah, they tell you to find.
Okay, this is not that bad though, and then this is where I like it. This part's great. I'm gonna take a seat actually. This is just basic 4-3-2-1 stuff. If I ask you to find the expected value of u min or whatever the fuck it is, I don't know. How do I find if I told you f of x was e to the x whatever? How do I find the I should say on something like say negative x on 0 to infinity? If I wanted you to find the expected value of this guy's distribution, how would you find that?
Multiply by y.
Yes,
Yeah,
multiply by y.
integrate.
So
Integrate y multiplies by y.
y times 2, right? Is it how old is this stuff? Is this something you did back in 4-3-2-1?
Yeah,
right?
no, it is.
And you're doing a little bit too as well, right?
Mhm.
So you do y times this guy, you're integrating from 0 to 1. Technically from negative infinity to infinity, but the distribution only exists on 0 to 1, so there's no point in doing that. This would be integral of 2y would be y squared. This would be 2 times negative y squared would be negative 2y cubed over 3. Plug in 1, plug in 0, and you get 1/3. Good?
Mhm.
How would you find the variance? Using
The formula.
variance formula, right?
Yeah. You have
expected value of x squared, so to do another integral, you need a y
For y
squared
squared.
here. That would give you
Gotcha.
2y cubed over 3 minus
Okay.
y to the 4th over 2. Plug in 1, plug in 0, that would be 2/3 minus 1/2, stuff like that, and go on. So
Okay.
cool. Let's look at 6.74. y1 through yn be independent uniform, and it's uniform again, so we can probably skip it. It's probably the same deal, because it's just, now instead of 2, it's with n. 6.8. Beta distribution. Shit, 6.8.
Yeah, this is a bitch because you gotta do all them integrals. You want to do 6.8?
Yeah,
But would he make us? Well, now we do have 2 hours. Is it the same amount of questions within 2 hours, or is it like more questions?
That's definitely going to be more questions.
Don't know. Let's find out.
Because
Alright,
that's
let's
like a
go,
very
let's
long integral.
Well, last semester his test didn't go like
Yeah.
to the same.
Because then you have to do like by parts, like integration and everything to get your answer on this.
Beta distribution with alpha and beta both 2. So that means what? It looks like this. It's shit. X squared, 1 minus x squared, and then there's some constant here.
Yeah, it's like that's
Gamma of
the
alpha
gamma.
plus beta over a gamma of alpha times gamma beta, right?
Yeah, exactly.
Or is it 1 over that?
No, you're right.
Okay. Oops. So this is something's not right. I don't think this is right. Oh, maybe we just okay. Gamma of 4.
Yeah,
Gamma of 2.
that's exactly how it is.
Gamma of 2. I believe gamma just means, as far as the whole numbers go, means factorial, right? What is gamma of 2?
It's like an integral. Or
No,
something.
no.
Oh.
If it's a whole number, then it's a factorial,
Gotcha,
I believe.
yeah.
Can you check out the gamma function? I don't know if it's factorial or
Actually,
mine's
might
one
be right
factorial.
because we did the integral earlier.
It's probably pain in the ass.
Yeah.
But
So-
look at
The
Wikipedia.
gamma
Just do Wikipedia.
function, we're
Yeah.
looking for the gamma.
N. Gamma of.
Yeah, right there. Gamma.
So it's 1 over gamma of alpha times.
No. I just want to know what this. What is gamma of n? Is
Oh,
that in factorial?
we got-
Or is that in
it's
minus
like
1 factorial?
chapter 6.
Wolfram Alpha will tell you. It's like gamma of 4.
Alright.
gamma of 4. 6, so it's n minus 1 factorial. Okay? Gamma of n is equal to factorial. So what would gamma of 4 be? That's 6. We just found that out.
Oh, so because we were doing it earlier, and we were doing the integral. We're like, oh,
Okay.
this is so long. Like,
Gamma of 2 would be 1 factorial. Times 1, so this would be 6.
Oh my god!
Yeah.
Thank you. That's what I wanted.
I knew there's a shortcut.
Okay, so and do the integral of this guy. What is the integral of integrate? Actually, I'll type it in. Or you got it. Integrate 6x squared times the quantity 1 minus x squared. Oops, close and then squared.
oh, minus x and this.
Quantity squared, yep. And then from 0 to 1. And we should get 1. Got 1/5.
It's close.
The hell?
Are we missing something?
Is this? Oh, is it +1 up here? Oh, it's
I
plus
don't
1.
I think so. But I do
Can I
think we're
see?
missing
This is the.
Beta
when we
distribution.
integrated, right?
Oh, alpha minus 1, beta minus 1.
Yeah, that's what it is.
So alpha minus 1 is 1, beta minus 1 is 1.
Yeah.
So that means this is more like gamma of 2, gamma of 1, gamma of 1.
Nah, that's still right. That one was still right.
Yeah, that I remember.
Right, but this which means this number is going to be different. This is just going to be 1 over 1 times 1, which is 1.
Oh, well, it does cancel out.
Oh!
Like when you integrate.
I see.
Yeah.
These numbers are still right, you mean. Right.
Yeah,
These numbers are still right.
My bad. This is 4, this was a 2. This is still 6.
At the end of it.
Okay.
Yeah.
Yeah. 6 over 1.
Okay.
Okay, yeah, we're good. Okay, so this is the PDF for the beta distribution of alpha is 2 and beta equals 2.
Yeah.
All right. Now, we want to find the distribution for the max, right? I don't know the problem anymore. Do you have the problem in front of you?
Yeah.
Sure enough, it equals 1. Cool.
I missed. Why is
Wouldn't we
it?
have to integrate this because it's part of the formula?
What's
is
that? You don't have to integrate. I was just telling him to check.
Why does? How do we get the?
Oh, I was talking about the next step.
Yeah, maybe.
Okay.
So
Probability density function of max. So
Probably
max.
distribution function. Probably distribution function.
So we have to
Yeah.
integrate max of this would be n times.
And times.
Shit, we have to integrate this in a second.
Yeah, because we need big F, the
This
distribution
is
function.
6 times x times 1 minus x.
Uh-huh.
We're going to need to integrate 6x
1
minus
minus f of-
6x squared dx. Which
That's
is
1 minus F. of
Well,
x
if
instead
we
of-
we could just
No, it's not.
remember.
Now, pause here for a second. You guys might be thinking, holy fuck, how am I going to integrate this to find the CDF, right? This isn't bad, because what is this as it relates to this?
That's F of Y.
Right.
Yeah.
But what is this? What did I just do? Remember, what did I just do to get
The
this?
chain rule?
You're on the right track, yeah. What is this as it relates to this?
That's
That's
the
probability
derivative of that.
density.
That's the derivative of that. So
Oh,
when
it's
I
the
integrate
rule-
this,
Yeah.
this would be a u. What would this be?
du.
Du.
Yeah.
What's the integral of n u to the n minus 1 du? That would just be u to the n, right? If I integrate u to the n times u to the n minus 1, I just get u to the n.
It's working backwards.
So
Yeah.
this just gives me
Okay.
3x squared minus 2x cubed n, and that's my CDF.
Yeah. He wrote in his notes that this is lowercase g of n, and then capital case g of n, which is what we just found is just f of y to the n.
Yeah.
So if we
Right.
remember that, we
Right.
could
That'll
probably
work
just
too,
plug
right?
it in, yeah.
And again, most of the questions you're going to be dealing with deal with either the max or the min. Rarely is it the case that we care about the order statistics that are one above the max, or one above the min, or one below the
Yeah, I
max.
remember thinking you talked about it.
It's very rare that they ever care about those. And if you see it, just skip it. We're probably better off spending more time doing those other problems than doing one like that, where it's not the max or the min. I believe it's 9:59, so I'm gonna head on out.
Okay.
Cool.
Sounds good.
When's your test?
Tomorrow at 8:20 p.m.
Yep.